Welcome back. This is the Mock 1, question 2, component 3. And here my ruler and calculator are going to come into their own. So I can see that there's a gap and know I'm going to have to do this E word and calculate something. And what are we calculating? We need to know the magnification. Now I think that a lot of you, when you see a calculate magnification thing, you start doing that IAM triangle. And you start measuring all sorts of things across trachea and, you know, don't look at what you're actually doing. It says calculate the magnification of the photograph. And here you've got a scale bar. You don't need anything else. You don't need to measure anything else. You have an image, the scale bar, and you have an actual size. So image over magnification, image over actual size. So, use the scale bar. So first of all you need to measure your scale bar, so I make that to be 25. Might get away with 24, I think it's 25. And this is just, if you find this question on the Eduquas website, because I think it was off last year's paper, maybe the year before, it'll give a different answer, and that's just because of the photocopying. So measure the scale bar, so 25, and it's in millimetres because I've measured it in millimetres, over 5, and again millimetres, so we're in the same units. That's the thing to watch out for. You know, if you've got micrometres here, you're going to need to make everything into micrometres. We haven't on this occasion. So 25 shared by 5, it's 5 times bigger than it is in real life. If you've got 24, obviously you might need to do some rounding. Let's just check that. 24 shared by 5, 4.8. Always remember, give your answers to 1 decimal places or 2 decimal places, unless you're told otherwise. So, explain how a feature visible in the photograph. So, I need to look at the features in the photograph. It's not the clearest image, but I can just about see there a ring of an incomplete. I'm just going to draw it on so that you can see as well. I'm sure it'll be clearer in the exam. C-shaped ring there. It ensures the trachea can function effectively during inspiration. So remember, when inspiration happens, the air pressure is decreasing. So explain how a feature, you need to state what the feature is first. The C-shaped ring of cartilage. Oh, I can't spell cartilage. AG. So I've forgotten everything over the summer, like you. Holds the trachea open, and this is again, it's straight out, you know, it prevents collapse of the trachea. As the pressure drops. And this leads us handily into the next bit, because we've been talking about pressure and collapse under, and if you were talking about xylem it'd be negative tension. And on the next page we've got a lovely, lovely graph showing how the air pressure changes in the alveoli. So they're getting you to think about pressure, and then they're going to ask you about it. So the graph below shows how the air pressure changes in the alveoli. And we've got here, because we wouldn't ever consider doing anything with a graph till we've looked at it, this is breathing in, where it's below the line, and this is breathing out and it's above the line. So what's the line? It's atmospheric pressure. So if the pressure in the alveoli is lower, than the atmosphere, you're going to breathe in, and if it's higher in the alveoli than the atmosphere, then you're going to breathe out. So, with reference to the graph, explain how the muscles involved in inspiration, so we're only talking about this bit, bring about the changes in pressure. So how do we get those changes in pressure during inspiration? So, we've got two sets of muscles involved in inspiration. Again, this is straight out of your notes. So, the external intercostals contract, and remember, you have got your own body in the exam with you. If you can't remember, you stick your hands on your rib cage and take a deep breath in. So, external intercostal muscles contract, and the rib cage moves up and out. And then don't forget, we've got another muscle, the diaphragm contracts and flattens. Now I think that's only going to generate you 1 mark because that's the muscles bit, so that deals with that bit. And then we need the changes in pressure. So, as a result, the volume increases in the thorax and pressure decreases to -1 AU. So now I've used some numbers from my graph. As the pressure is below atmospheric, air flows in. Where does it flow into? Into the alveoli. Lovely. So we've looked on the muscles, why the pressure changes, and what that means in inspiration. Fantastic. So, part C. The graph below shows how the partial pressure of oxygen in blood changes as blood flows through the pulmonary capillaries. So as it's going from the pulmonary artery round to the vein, it's picking up oxygen. So, we've got the partial pressure of oxygen in blood, length of capillary, it goes up really quickly, and then it levels off after, what, just under 25. So, describe, what do you see on the graph, and explain. So that's nice and easy. So, the partial pressure of oxygen in the capillary, this is my description, increases. I've got a graph with some numbers on, so why wouldn't I use it? From, what do we reckon that is? 8, 9, 10 squares for each. So, 5, 6, 7, 8, 9, 10. So my scale's 2 squares to 1. So from 5.5 kPa to 14 kPa. Yeah? and then remains constant. Now do be careful here, because I know your big temptation is to refer to time. There's no time on this graph, it's the length of the capillary. And the other big temptation is to say, and then stops, but it doesn't stop, it's just level, and at its most. So, why is it that shape? So it's rapid increase as there is a big concentration. Large is probably a better word, but I haven't got room. I've written in the forbidden bit. So big concentration gradient at first, and levels as equilibrium is reached. I really can't write. And I'm again writing in the forbidden. Don't do this in an exam, really, because it just gets chopped off. Nobody will be able to see what you've written. So, what conclusion could be reached about the minimum partial pressure of oxygen in the air in the alveoli? Explain your answer. We've got a couple of lines to do that. So, obviously, if we're saying it's equilibrium, it's got to be 14 kPa at a minimum. How do we know that? Because equilibrium, and you can see, it's still got, 75% of its capillary to go. It's reached between the blood and alveoli. Describe the features of the capillary that allow this change. So what's great about capillaries that allows diffusion? So walls of capillaries, and be careful not to imply that those are cell walls. They're not. It's a tube wall. One cell thick. Don't be afraid to write these simple answers down. A short diffusion pathway. So when you've got these nice simple answers, you must explain what the significance of those features are. But it's just a description. What else could you put? Many capillaries give a large surface area. Again, for diffusion. And the other thing you could refer to is that sort of idea of it being very thin. You've got a very small diameter to give time for diffusion. Quite often ask for 3 of these. They're only asking for 2 in this case. More time for diffusion as blood flow is slowed. Now you might not need all of that detail. They might have just wanted you to say, yeah, the wall's one cell thick and they've got lots of capillaries, but if you don't actually explain that you know what's going on, if they did want more, you're going to lose the mark. So you should always write a really full answer. Don't be lazy with that. So, diagram shows the arrangement of blood vessels in a capillary bed. So here we've got the artery bringing blood in. We've got the capillary. I think you've got a picture like this in your notes with little with the cells of green in between. and it goes from red to blue. We've got the blood flow going through, we've got the body cells, and we've got the tissue fluid all labelled for you in the vein. So, with reference to the diagram, describe how tissue fluid is formed. So, what do we know about formation of tissue fluid? What forces the fluid out? It's that difference between hydrostatic and osmotic pressure. Remember, sort of, we kind of drew it on the board like that. Hydrostatic pressure out, osmotic in, and then at the other end, the venule end, we've got our osmotic in and hydrostatic out. We're only talking about this end. So, at the artery end, the hydrostatic pressure exceeds the osmotic. And you can call that pressure, or you can say water potential gradient. It doesn't matter which way you do that. Water and small molecules are forced out and cells and large proteins remain in blood. And that's pretty much all you can say about the arteriolar end. Sometimes they'll ask you to go on and explain what's going on at the venule end, but not on this occasion.